So thank you. First, I would like to thank you, the organizer, for inviting me. I'm very excited to celebrate the Year of Soil. It's a very nice initiative. So I'm working at the University of Copenhagen, and I'm going to show you two examples of study we are doing there. First, I'm going to start with this global carbon cycle. As the first speaker said this morning, soil contains a lot of carbon. So the entire soil is 2,300 gigatons of carbon. And that's basically much more than the atmosphere and the plant biomass combined. And the first speaker also said it has been said recently that 4 per mil annual increase in soil carbon can basically offset the annual emission from human beings, which are these 9 gigatons of carbon. So even a very small increase in soil carbon can be very important. So it's important to design all the practices that can increase soil carbon. So here I'm showing you the environmental effect of soil carbon. So basically, when you return crop residues or you apply some organic waste products to the soil, then you can increase your soil organic matter. And this has a lot of environmental effects. So many of them are positive, like carbon storage, increase of aggregate stability, increase of soil porosity, and also providing nutrients to the plant. And also some of them can be negative, like soil contamination and leaching of nutrients to the groundwater. But as you can see, there is more positive effects than negative effects. So it's important to increase soil organic matter. So the first example I wanted to show you is it's a study we conducted on the impact of exporting wheat straw on soil organic matter and what alternative management practices can we use. So as you may know, the wheat straw is more or less is more and more exported from the field to produce biogas, to produce bioenergy. So it's nice to produce bioenergy, but then you may run into problems for the soil because then you have less residue to incorporate. So the export of the straw residue may reduce soil carbon stocks. And we wanted to study the effect of exporting the straw and also the effect of introducing alternative practices like a catch crop or sowing wheat early sowing of wheat to offset some of the loss occurring when you export the wheat straw. So that's the objective: estimate the change in carbon, explore the potential of these alternative practices. And also we wanted to illustrate the starting point of the soil. If you start with a soil with a lot of carbon or with a soil with very low carbon, then you will have different results of the different practices. So to do that, we use a simulation model, the DAISY model. It has been devised, created at Copenhagen University. And we use different scenarios with different cropping systems. So the cropping we use is a continuous wheat straw cultivation, so monoculture of wheat straw for 100 years. I know it's not optimum, but it's just to see the effect. It's a case study. And we use 5 levels of initial soil carbon from 1 to 3%. That basically reflects the past organic fertilization. And 3 levels of straw incorporation, 0, 50%, and 100%. And with or without a catch crop, and 2 sowing date of the wheat, 1st and 22 of September. So 22 is the normal sowing date, and the 1st is the early sowing date. So these are the results. And as you can see, after 100 years, if you export all of the straw, so 0% incorporated, you decrease a lot the soil organic carbon. Whatever the starting point you start with, you will decrease the soil carbon. Then if you incorporate some of the straw, you will either limit the loss of carbon or increase soil carbon, depending on the starting point. So here you can really see that incorporating straw make a difference for the soil carbon. And now if you compare with the catch crop and early sowing, you can see that these two practices can help to mitigate the loss of carbon occurring when you export the wheat straw, but still you will lose some carbon, so it's not completely optimal. Now these are the results for the nitrogen leaching to the groundwater. So here you can see the scenario with all the straw exported, and you see that you increase the nitrogen leaching with increasing the soil carbon. That's normal because every year soil organic matter decomposes and some of the nitrogen is released and it might be leached to the groundwater. But when you compare to the catch crop and the early sowing practices, you can see that with those two practices you can decrease your nitrogen loss. And the same applies for N2O emission. You know that N2O is a powerful greenhouse gas, and you can decrease N2O mostly with early sowing of wheat because then the soil is not bare so long, so it has a cover for longer, and this is important. So the conclusion of this part, exporting the wheat straw has an impact on soil organic carbon. It decreases soil carbon, so it's important to at least incorporate some of the straw and not use everything for bioenergy crop. Cultivating a catch crop and early sowing can offset some of this loss. And this can also reduce some of the nitrogen leaching and N2O emissions. So that was the first part, and then I wanted to present you another example, which is a study we conducted on the reduction of fuel consumption for soil tillage by applying organic amendments. So here I show you again the environmental effect, and here we address mostly the positive effect related to porosity. So when you apply organic material to the soil, it makes it lighter because the organic matter is a very porous and light material, so it makes the soil lighter. And basically we thought that making the soil lighter might influence the fuel you use for making the tillage, because then the soil is not so resistant to the tillage operation. So to test that, we used a field experiment, which is in Tostrup. It's 20 kilometers from Copenhagen, and we have this field experiment. It's a sandy loam soil, and it was started in 2003 with a spring and winter cereal rotation. And basically in this field experiment, every year we apply some organic waste, so different type of waste, bio-waste, household waste compost, sewage sludge, human urine, cattle manure, deep litter, cattle slurry, which are compared with a conventional NPK fertilizer and green manure, and also an unfertilized treatment. So what we did is we went to the field with this fancy tractor, which is mounted with spring tines, and these tines are related to some boxes that record the force you need to pull the tractor. So it's basically recording the energy used for soil tillage. And then we simply drove across the plot like this and measure for each treatment the energy required for doing the tillage. So these are the results. First is soil organic carbon. So you can see that for the different treatment, you have huge difference in soil carbon from the NPK and unfertilized, which of course has the lowest level, to the compost and accelerated compost. So the accelerated rate is 3 times the normal rate of compost. And you can see you basically can increase a lot your soil carbon with this organic waste. These are the energy used for tillage results. We call it specific draw. So the draw force for the tillage. And you decrease this force with applying the most stable waste. So here you can see that's a function trying to estimate the energy for tillage from clay content and soil organic carbon content. And it looks complicated, but basically this function can explain 67% of the variance in the energy for tillage. And what it's telling us is as you increase clay content, you will increase the energy you need for tillage. And as you increase soil organic carbon, you will decrease the energy you need for tillage. And if we transfer that to in terms of fuel consumption, so this table shows you the fuel saving as a difference compared to the NPK treatment. So we take the NPK as a reference, and we calculate the difference in fuel consumption from the NPK treatment. And you can see some of the treatments only lead to a small saving, like 5%. And the biggest saving are for the biowaste compost and the accelerated biowaste compost, where you can save up to 14% or 25%. So it can be a substantial saving of fuel, which is, of course, is interesting for farmers and also important for climate change and reducing fuel consumption. So conclusion for this part, the energy used for tillage increase with the clay content and decrease with soil organic carbon content. Applying the waste can save up to 14% for the compost, which is quite stable material, of tractor fuel for the tillage. And thank you for your attention.